And so you should be able to see the problem. I'm sharing the screen. It says the double pulley shown has a mass of 15 kilograms, and they're given the centroidal radius of gyration is 160 millimeters. And so whenever you see that, you know that you're going to use the I equals mk squared equation, where k is the radius of gyration and m is the mass. And then they give you the coefficient of friction. And so we're given it's at rest. And we want to know, again, how far is block B going to slide up the hill once block A hits the ground, and how fast is block A going when it hits the ground. All right. So that's the overview of it. So let's go ahead and let me go back to my dot cam. There we go. So there's my dot cam. Hopefully it'll behave a little better than last time. So here's our drawing. We have I've calculated our I with using mk squared, 15 times 0.16, we get 0.384. And then there's our drawing with our respective radii. So first thing we want to look at is the fact that the block A and the block B are not going to move in a 1-to-1 ratio because of the different radii of the two. And because of that, we have to figure out what that is. And it turns out that you can calculate that just by looking at the ratios of the, just by looking at their respective ratios. So for example, we know that the velocity of A equals the radius of A times omega C, where omega C is just the rotation of this. And we know that the velocity of B is equal to RB omega C. And so since we have the like values, we can solve. And so therefore, we know the velocity of B equals radius of B over radius of A times velocity of A. And so we know that relationship there. And so later on, we'll use it. But if we were to take, essentially, we know the velocity of B is going to be 0.150 divided by 0.250 velocity of A. And I believe that is, I have it right in front of me. Yeah, it's 0.6. That's right. It's 0.6. So we know that the velocity of B is equal to 0.6, the velocity of A. All right. And that makes sense because it's at farther out on the radii. All right. So the other thing we want to do is we want to, since this is an energy problem, because we're given velocity, we're given distance, so it makes the most sense to use energy in this one. For one is we know that our T initial is 0 because we're at rest. So everything's at rest, and then we apply this P, and the P value is, P is 150 newtons. Sorry, I'm going off my notes and I didn't write that down. Back on the other way. 200, sorry about that. So we know that this P here equal 200 newtons. All right. So first thing is we're going to figure out what is our, we have T1, and then of course we have our T2. That's our state later in the, after it's been moving. And so you may recall when we did energy in the past, sometimes we would do these generic relationships where we would say T2 is going to be equal to 1/2 ma VA squared. So that's just the mass times the velocity of A. And this is going to be at the point where it hits the ground. And then that's also going to have to be equal to 1/2 mb times VB squared. And that's just the kinetic energy of block B. And then we know that that's also going to have to include the rotational inertia of the disk or the pulley. So that's going to be plus 1/2 IC omega C squared. All right. And so with that, what we can do is we can simplify this, and we can write this out as a relationship between, so ultimately I want a relationship between the kinetic energy at the end and the velocity of A at the end. That's what I'm striving for here. So what I'm going to do is I'm just going to do some substitution. I'm going to say that if I factor this out, I get 1/2, and then I have 5 kilograms, and then I'm going to have VA squared. Actually, I'm not going to factor at this point. Then I'm going to say 1/2, and that's 15 kilograms. And now my VB, remember what I said is up here, I said VA and VB are this. So if I want to put VB in there for VB squared, I can just do this. I can put 0.15 over 0.25 times VA all squared. So all I did was substitute this relationship for VB down here into that. All right. And then I also have plus 1/2. And then recall that I calculated my IC. So IC was just 15 times 0.16 squared. So that was just the mass times the radius of gyration squared. So I got 0.384. So I'm going to go ahead and bring that down here into this value, IC. So I'm going to write that as 0.384. All right, so far so good, I hope. If I'm going too fast, just say, ask questions, don't be shy. And then the last thing I have is the relationship of omega C. So remember that that when we're dealing with the if we want to substitute omega, we can use the relationship that omega C equals the velocity over the radius. Remember that general equation there. And so so if we, knowing that, what we can do is we're essentially going to factor out VA, because we know that if we write VA up here, as we had this relationship, what this ends up being is 1 over 0.25 squared times VA squared. And so this relationship here is my equivalent to omega C. All right. And so I can get that by just substitution of this, using this and some substitution. That's how I got that. So if that's not readily clear, just play around with that and you'll see what it is. It's not a complicated substitution. So what we end up with then is we could also, if it's easier to see, I could have just used the generic terms, and I could have just said that T2 equals, factored out the 1/2 VA squared, and then just written it as MA plus MB RB squared over RA squared plus I of C over RA squared. Okay, and that's just another version of it. Anyway, the point is that you want to, the only substitution really that we're doing here is we're saying this for that, and we're using this relationship between omega V and R to get rid of the omega and put it in terms of VA. That's it. And in order to do that, we have to manipulate a little bit, but as you can see, the whole objective is to get it to the point where the only unknown we have is VA. Otherwise, we have two unknowns. So if we substitute in, let me get a little shadow. That helps or not. If we substitute and go ahead and solve, then as we did, up here, if we solve for this, we get T2 equal to 8.272 VA squared. All right. So we have this relationship. So that's our energy as related to VA. So we're going to hold that for now. And that's just has to do with this moving down and that moving up. All right. Okay. So next step is, if you go back and look at this, you can see that if we look at our energy, our U1 to 2 that we usually deal with, what do we have? So if we think about it, we have the change in elevation of this, we have the change in elevation of that, we have the motion of friction there, and we have the force over distance. So we have 4 different things going on. So let's go back and look at that. So our U1 to 2, and we're doing this kind of piecemeal. We're doing T1, then T2, now U1 to 2, and then we'll put it all together. And I'm not saying this is the only way to do it. If you want to put everything together at once, if that's easier for you to see, by all means. But what we have then is P times the distance SA. Now, SA is really just this distance here. It's this distance going from here to here. How far is P going? It's going 1 meter. All right. So force over distance. So we have P times SA plus the mass of A times G times the distance SA, because that's the motion, is the object drops potential energy and gains kinetic energy. And then we have to subtract the friction. So the friction force, F times SB, that's just the distance SB. Now SB would just be this appropriate distance up here. So if I label it, maybe that's better. This is SB and this is SA. All right. Make sure you have that down. Sorry, I keep going back and forth. I wish I had a bigger screen. All right. So going back to here, we have PSA, MA, that, and then we also have we have to go uphill. So mass times gravity times SB times sine 30. All right. So there's our total change of energy. So the force times distance, the change in gravitational of block A, change in gravitational block B, and the friction. All right. So we can plug in these different values. Now we know that this is going to be 1 meter. We know that's going to be 0.6 meters. And so we need to know, what is the frictional force? So the frictional force, I'm going to do that on a different sheet, and then we'll come back to this. So we know the frictional force because the block is sitting on an incline like this. And so if we were to draw our free body diagram, we know that that's our normal force. We know that that's our friction force. We know that that's our mg. And then of course, we know we have this going that way. So we're really only interested in this part of the free body diagram. We're not concerned so much with the tension here, but we want to know what our friction force would be. So in this, if we sum the forces in the y, where this is the y and that's the x, to 0, because there's no acceleration in that, then we know that n just equals mg cosine theta. All right. And so with that, we can write this as 15 kilograms times 9.81 times the cosine of 30. root 3 over 2. And so we get an n value equal to 127.3. And since mu kinetic was 0.2, we know our friction force is equal to 25.46. Okay, so we know it's 25.46 newtons. That's all we need to know with that. And so we're going to keep that value. All right. And then, so now let's go ahead and we'll assemble our U1 to 2. So our U1 to 2 then, again, recall is equals P SA. So what's that going to be? That's going to be 200 newtons times 1 meter. And then we have plus MA G SA. So that's going to be our 5 kilograms. So plus 5 kilograms times 9.81. And then times SA. So SA being, again, 1 meter. All right. And then minus my friction force. So we know my friction force is going to be the friction force times SB. And that's going to be minus 25.46 times my SB. And what's my SB? That's 0.6, because that's how far B moves. All right. And then lastly, minus the mg sine 30 times SB. And so then the gravitational. So last one is just going to be minus my 15.
Yes, sir.
Yes.
Would you need to add the x component of gravity for your F times D as well?
That is the x component of gravity. What are you referring to?
Oh,
so if we look, so I guess going back, this PSA is the force. That's my y component of gravity due to of A, right? This is the friction, and this is the component of gravity of the 15 kilogram block.
yeah, but then there's also, because that's like the gravitational potential energy, right? That last term.
Yes.
So then, but then there's also the component of gravity that's pushing it like horizontally down the slope, and wouldn't
that's what
be
this is. That's what this is.
Okay.
See, if you have something like this on a slope, right? And here's your block, then the amount of force going down that way is going to be mg sine 30, right? If this is 30 degrees.
Wouldn't that be cosine 30 then?
Cosine is going to be, because remember how it's going to look like this. It goes like this, this, and this. So that's the normal force is the cosine, that's the sine, and that's the hypotenuse, which is gravity.
Okay.
So yeah.
Okay.
So,
yeah.
Does that make sense?
Yeah.
Okay. Good. So yeah. So this is the accounting of the gravitational force. So you have the m, the g, and then we have 0.5 for sine. So I run out a little space there, and then lastly we have the distance, and that's 0.6. So we have everything included. So if we add all this up, then we end up with a total U1 to 2 equaling 190.2 joules. All right, so now we have that as our value. So what we can do now is we can go back to our original equation. Remember that what we found earlier was we found that T2 equaled 8.272 VA squared. So now we can just write this as T1 plus U1 to 2 equals T2. And so now we can just say 0 plus 190.2 equals 8.272 VA squared. And now we can solve for VA squared, or VA. So VA ends up being 4.80 meters per second as it hits. All right. So you see how we included everything in this problem. We included the rotational energy of the disk. We included the friction. So this pretty much is, there's nothing other than putting a spring in this problem. There really isn't anything more we could do with it to make it complex. All right. So I think if you can follow this whole problem and do it, then you should be in really good shape for any questions on the final that are given that are like this. So we're not done yet though, because we still have to determine how far does it go. So we can then, we know that if VA is 4.8 meters per second, we can then also determine then that VB, that recall is going to be equal to the ratio 0.6, because that's the ratio of the radii times 4.8. So we know that VB when A hits the ground, VB is traveling at 2.88 meters per second. That's important because that's going to tell us how far it's going to continue to slide. So we want to then set that up as kind of another energy situation. So we'll write that as T3. Oh, and then we should also figure out what omega C is, sorry. So we know that omega C, because when, and this again, omega C is when A hits ground. So that's important. So when A hits ground, omega C is going to equal VB over RC. Okay, or it could be VA over RA, it doesn't matter, it'll be the same ratio. But so we end up with 2.88 over 0.15, and we get omega C equal to 19.20 radians per second. Okay, so it didn't ask for these two values per se, but we need them in order to find the subsequent distance it's going to move. So with that, we can write then, we know that it went at least 0.6 meters, so total distance is going to equal 0.6 plus, and that's what we're going to find. So if we write that out, we're going to say T3 equals 1/2 MB VB squared plus 1/2 IC omega C squared. So notice that this is the same as what we wrote for the beginning. We just don't have A anymore because A has hit the ground, and so it no longer has any kinetic energy. It's considered stopped. And so it's not going to have any influence on the remaining kinetic energy past that point. So if we go ahead, in this case, we have all our values here, so we can actually find the kinetic energy for this. We can put in 1/2 15 times 2.88 squared plus 1/2 0.384 for IC, and then we know omega C 19.20 squared. And so we end up with a total of 133.0 joules. So there's my energy for 3. So last thing, now we know that the final T4, that's going to be equal to 0. So really we know that it's going to be T3 plus U3 to 4 equals T4, where we know that that is 0 because everything's going to stop. So now we really just need to figure out what this final friction distance is, and that's that. So really our only unknown is this this distance. So if we write U3 to 4, we get negative friction force times, we'll call SB prime for that additional distance, and then that's going to also be minus mg sine 30 times SB. Okay, so if we go ahead and put in our values, let's see, we have, well, essentially we have all our values. We have minus 25.46. And then what I'm gonna do is I'm gonna factor this out. So minus 15 times 9.8 times 0.5, and then all of that is going to be times SB. So I just factored out the SB out to get me that. So I end up with essentially minus 98.96 SB prime. And there we have it. So we can then say 133.0 minus 98.96 SB prime all equals 0 for my T3 plus U1 to 2 equals T4. All right. So a lot of steps, took us a while to do that one, but you can see hopefully that it's actually pretty systematic in the solving. There's nothing really super secret to it. It's just it just requires good consistent work throughout the problem. So if we go ahead and solve, we get SB equal to 1.34 meters, SB prime. So we know the total distance is going to be plus 0.6. So S equals 1.94 meters. And there's our answer. All right. Any questions on that? Make sense? I didn't expect that to take a half hour, but I guess it did. But I'd rather have you understand one good problem than a bunch of smaller, easier problems.
Excuse me, Professor.
Yes.
Can you please explain again the part of the sine 30 for the one you explained before? I think I didn't get it.
Oh, okay. So when if you're going uphill, let's see. Let me grab my ruler. Anyway, so if you're going uphill, remember that if you draw your vectors like this, so that if that's whatever this angle is here. So we know that normally when you write this, that this is your gravity, right? That's mg. So this side here is mg sine 30. And that's that part of the vector. So the vector looks like this. Gravity, this part of it's normal. So we equate that to the normal force because it's perpendicular to the surface. This is the part of gravity that wants, this is the force of gravity wanting it to go back down the hill. So when we did the problem, remember we had our block and we're trying to pull it up the hill. So we have to overcome that. And so what we're saying is this is really just the change in MGH. That's all this is. So if we want to go from here to here, this distance, then that's going to be whatever that distance is times mg sine 30, and that's equal to our potential energy. Does that make sense?
Yes, thank you.
Okay.
So you could have also just taken just like the mg by itself and then just found the vertical distance.
Yeah, you could have done that. That's true. I usually just multiply it by the sine of whatever the angle is. But you're right. You could have figured out that horizontal. But you don't know because the horizontal distance, or I'm sorry, the vertical distance changes with the horizontal distance. So you don't really know what that is, right? You don't know. I mean, you knew S. You could calculate if it's moving 0.6 meters, that means it's going to move so far in the y direction based on that proportion. But in the final answer, you don't know exactly how far it's moving because you don't know what S prime is. You're solving for that. So you can't really solve for it directly. So you just write it as it's going to be S times whatever MGH is, or MG sine 30. because that's what h is. It's mg sine 30. Okay. All right, so let's go to so I want to talk about momentum now. This is section 17.2 in your book. So in 17.2, and this is just the theory behind it, but what and you've seen this before. We know that if you have it doesn't matter if it's a single particle or a rigid body. When you're dealing with momentum, you have your system, which is here A, and then you have some external impulse, which is your force over time, and that results in your final momentum. And that's really all it's saying. And it could be due to an impact. It could be due to a force that's applied. So there's all different ways to write momentum. And we see that whenever you have a problem where you have time in it, that's a good indicator that you want to use momentum. Because remember, as I said on the final, you're not going to be told this is from chapter whatever, and so this is what you should use. You're going to have to surmise that based on what's written in the problem. So remember too that that momentum, angular momentum, is the moment of momentum, and that'll become an important part in problem solving, because you want to understand that if you have angular momentum, it's really whatever the linear momentum is times that distance. So here what we have is a series of MVs, and we can write those as multiple vectors on the left of, so where we have a multiple vectors with MVs or multiple momentums acting on this, and those all can be equated to a single momentum from the center of gravity plus the angular momentum, which is just going to be equal to IW. And so that's a way to shortcut that if you have a bunch of arbitrary forces, arbitrary momentum acting on a rigid body. And so the summing part is probably the most important. And so what I mean by that, let me just find that sheet. Right. Bear with me for a second. Maybe it's in the next slide. No, it wasn't in here. Something I wanted to show you specific to it. So I'll just pull it out of the book because I had it written down here. Chapter 17.2. So hopefully you guys have looked at this section, but it's at the end. It's something that's right here. So let me go ahead and stop my share and point out to the fact that when you're dealing, remember that when you're dealing with momentum, just like before, remember how when we would do our sum of the moments, when we're doing F equals MA, we'd have sum of the moments about a point O equaled sum of the moments effective, so to speak. And so on this side, you'd have whatever the sum of the moments were, the forces, right? So this would be whatever those forces were acting about the point of reaction. So for example, when we had our problem with the bulldozer or the loader with the gravel, you took your moment about this point here and you figured out what all the moments were based on. So here you had this point times that distance, and you had this times that distance, and you had the center of gravity times that distance. And then that was on the left side of the equation, right? Then on the right side of the equation, you had essentially the I alpha. And if it wasn't rotating, you would then have the MAD perpendicular. Okay, so that should look familiar. Well, so with momentum, it's similar in that you'll start off with your I omega, because really what is that? That's like MV. So we're talking about if you have, any kind of rotational momentum, you have I omega, and then that's going to be plus the sum of your integrals of your moments about O with respect to time, dt. And then that is then going to give you your I omega final, we call that I omega initial. And so, but we can also have written that, and that's where you see the similarity, is this could have been I omega, and then this component here would have been written as mass times the distance to the R bar, that's the distance to the line of action, times omega times R bar also. And so what we notice from that is that this relationship here, if we write all this out, then this is really the parallaxis theorem, isn't it? It's saying that I plus mr squared times omega is the same as I naught omega. So what this is saying is that, and this is this term here, what this term is doing is it's essentially can be written as either the moment about the center of gravity with respect to time, or the linear momentum that's created about a point other than the center of gravity multiplied by the respective distance to the line of action. So that's a lot to chew on, but the application of it's actually not that difficult. It works out pretty well. So going back to
Professor,
yes.
So R is the distance between the center of gravity to the
point, the arbitrary point that you're taking it about.
Okay.
Yeah, that's the R bar. So it's exactly. So if we look at, go back to this. That's what, actually it's not in here, but you could see, actually let's do an example because I think that'll come out better like that. This one's actually a very easy example. In this case is that what we have in this one, and we'll mop this up on Wednesday because I know there's probably going to be some questions after this, so we're not going to be able to finish in the next 10 minutes. But but you should have enough to get through the homework based on what we've talked about today. So if we look at this example here, you have a uniform 75 kilogram cube attached to 70 kilogram circular shaft. And so it says, it gives you some data, and it says determine the time required for the angular velocity system to increase from 1,000 to 2,000 RPM. So this one, the math's real easy, but I'm just going to set it up because I want to talk about a different problem. But first off, if you have a cube, and then you have your cylinder like this, then we know that there's going to be our moment that's equal to 20 Newton meters. Okay, and so our cube is going to be 1/12, and again you'd have to be given this m times L squared plus L squared. That would be the moment of inertia for the cube, and then of course we know the cylinder is going to be 1/2 mr squared. So if we plug in the values we're given, we end up with I bar equal to 1.475. So our equation, our overall equation then is just I omega plus moment times time equals I omega 2. And so that's the thing I was trying to say earlier, but it may not have come out as clear, is that the up to this point with a rigid body, we haven't really talked about adding a moment over time. So you may recall that in energy, before what we said was if you did a moment times theta, then that was your kind of term in the middle, right? So you had U1, you had your U1 to 2 could be moment times distance. Well, now you have your momentum, initial momentum, right? So this is initial. And then now this is your integral of f dt. Only it's a moment over time, but it's the same idea as having a force over time, right? As we've seen with the way that momentum is presented, it's your initial momentum, and this again is angular. So we would either write it as mv plus integral of f dt equals mv final, initial, or we would write it as I omega initial plus mt equals I omega final. And the only difference is instead of up here with linear, this is force times distance, and here this is angular. It's going to be moment times time. I'm sorry, I didn't mean force times distance, I meant force times time. This is force times time. This is moment times time. So hopefully you can see that's the only difference between the two, is we're just using I instead of mass, omega instead of velocity, moment instead of force, time is the same, and then you end up with the same. So it's the same process. It's just in going in a circle. So anyway, to deal with this problem, we really just have I, if we solve for our equation, ends up being I omega 1 plus moment times time equals I omega 2. And so if we solve for time, we get T equals I bar times omega 2 minus omega 1 all over M, the moment. And so if we plug in, we have everything. We're given the initial and final omegas, we're given I, we're given the moment. And so we can solve for the time. And so I know you guys can plug numbers in. So that's 7.72 seconds. So not a challenging problem mathematically, but I liked it because it shows the concept of this really well. It shows how you have an angular momentum, you apply a moment over time, you have an increase, just like you would with linear. And I think that's the big takeaway I'm trying to get from this. If nothing else, that's what you want to understand.
Professor?
Yes.
So when you have a complex shape like that, the total moment of inertia is just the moment of inertia is added together.
Yeah, he used them as
Okay.
the, and in this one, we've specifically told you that you're through the centroid. So for example, you're like this. Sorry, my line's not very straight, but imagine that's right through the center. So this 1/12 ml squared is through the center. This is through the center of that shaft. So you have to be, we'll be pretty specific about that. So if you do use the parallaxis theorem on the final, it's not going to be anything gnarly. It'll be a very straightforward composite shape, if at all. All right. Okay, so let's look at this one. We can start some of it, and then we'll I'll plant the seed, and then we'll do this one in class on bright and early on Wednesday. And then we'll essentially, we're going to talk about momentum on Wednesday, and then Friday will be review for the final. So I don't think we need more than one period. I also want to give you your test back on Wednesday, so I want to have a little bit of time for that. But anyway, so in this one, you have this carriage and these objects. So I think this problem, the challenge for this is that you're going to want to combine your instant center with relative motion, which it sounds harder than it is, but let me just show you, since for lack of time, let me just show you what I've done so far, and then we'll do the full problem on Wednesday. So here we have a 3-pound carriage. C is supported by 2-pound uniform discs. So kinematics and impulse momentum. So that's what this is. So first off, we draw this. So this is our carriage. This is our instant center. So remember that anytime at a moment in time, whenever you're dealing with a cylinder, that point where it touches the ground is where there's no velocity. And so we can write our velocity A, which would be the center of the circle. And then we can write velocity C, which is where C and A meet essentially. And we know that from looking at this, that velocity C is going to be twice that of that, because velocity C equals omega A times 2RA. And we know that omega A equals omega B. These have to roll because they're not slipping. So we know omega A and B are the same. Therefore, velocity of B over 2R. So essentially, all this is just telling me that velocity of A is half of velocity of C. And I think you can see that relatively easily because this is twice as far up as that. So then if we look at our free body diagram and bring that into closer focus. So this is 0 because we start at rest. And then we have a force times time. We're told we have a point, I think 1 pounds over 0.2 seconds or whatever it is. And then we know that we have friction 1 times delta T. And we have friction B at times delta T, normal A, normal B. So what we're doing is we're essentially writing these values here for that. And then the final is just going to be MCVC. So the final velocity and the final mass going this way. And that should be a C. All right. So what we can then write is this relationship 0, because that's our initial momentum, plus P delta T minus F1 delta T minus F2 delta T, where I've just said A and B are 1 and 2, even though they should be technically the same. And then that all equals MC. So that's our first equation. All right. And then the next step is to draw these. And so these are the actual wheels. Now, when you draw the wheels, you know that you have a normal force times time. And this is important. You want to make sure that your free body, when you're dealing with this, has time, FA delta T, F1 delta T, N1 delta T. So what I did is I've put everything on there. And this wheel, this is for wheel A, but it applies for wheel B also. And then at the end, I have MAVA plus IGWA. Okay. All right. So we're about out of time, but that's how we got started. And then it's just a matter of plugging through the rest of it, which we'll do on Wednesday. So sorry we're out of time, but I hope you guys have a nice long weekend. And we will reconvene Wednesday. Actually, well, Tuesday, I'll be in office hours Tuesday if you need to talk to me before then on the homework. All right. Thanks, everybody.